Okay, so I'm going to have another go at going through the derivation of the Navier-Stokes. I'm aware that it was fairly quick yesterday. What I'm going to try and do is I'm going to try and actually do it on the board. So I'll at least be able to show you each of the steps, and obviously any part of this where you want to stop me, ask any questions, please do. And what I'll try to do is highlight at least the key steps of that process. So one thing we didn't cover yesterday was the derivation of the continuity equation. And if you look on any kind of textbook, that will be the first thing people cover. Part of the reason was just time. I didn't really want to kind of add an extra section in, but because at this point we've got basically today where we've got the hands-on session, but what I'll try and do is I'll try and start by showing you essentially Reynolds transport theorem. Reynolds transport theorem, first of all, for density, which will kind of introduce the idea of mass continuity. And then we'll go on and talk about basically the same derivation again, which then becomes basically a repeat of the same process. So hopefully by doing it twice, it becomes clear. So if you think about a molecular system as our kind of starting point, you have a kind of box of molecules which, you know, this, typically you'd have kind of periodic boundaries on each side, or this would be kind of conceptually an infinite system, if you like, or large enough that the edges don't matter. Now each of the individual molecules themselves are in their own kind of Lagrangian reference frame, so you're interested in the way these kind of evolve, and these evolve individually according to Newton's law. So what we can do with this system is we could arbitrarily choose a selection of these molecules. Let's say this subset. So this would be a system, effectively, a subset of the molecules in existence. So all the molecules in the universe, we're interested in, say, these 5. So let's say these are our system. So what that means is you actually have a statement where I equals 1 to ns, where this is implicitly saying this is the sum over the system. So sum of the molecules in that system. So the projector, did you have trouble with the projector yesterday again, or was it okay? It was okay. Strange. Okay, anyway, we don't need that, so we'll just do it all on the board. Maybe it's my laptop. Okay, fine. Right, we'll do it on the board. Okay, so this sum of the molecules would be equal to 0. Does that make sense? So if you're following these 5 molecules, they're never going to change. The amount of mass in there is never going to change. So each of them have the same mass, and the idea is that you follow those sort of same set of molecules, and it always has the same mass. Does that seem okay as a concept? Exactly, yeah. So what will happen over time is these molecules will all move around. And then what you'll see is that effectively this volume from that time to a later time, if you had to draw a volume around them, for example, would change in shape. But the actual, by virtue of this sum being limited to those set of molecules, this collection of molecules, trivially we have kind of conservation of mass, if you like. So this is a consequence of us being able to follow exactly the same set of molecules, which is fine in molecular dynamics because you're actually looping over the molecules in your system. You know exactly where they are. You're following each of them. And each of these is basically its own reference frame. So each molecule is, if you like, a Lagrangian reference frame. Okay, so the idea is to apply the same concept to the continuum, to have a kind of Lagrangian reference frame. So we talked a lot about a continuum and what that actually means. So this is a continuous field where, you know, this is some function valid, you know, at every position in x and y, for example. So you can define a value at every point in space. And again, you know, you've got boundary conditions at the edge, but we just assume for this particular case that it kind of goes on forever. And then we're only interested in, say, a subsection of that. So again, sorry, I'm going to be consistent with colouring. So the original system, if you like, is some blob of continuum. And that's arbitrary, but it's some collection of continuum. And you'll see terms like particle or element, but, you know, the idea here is that it's some collection of continuum. And then what will happen over time is this will then, you know, evolve and deform. So in the same way that, the molecules will move around, and then you can effectively consider that being, a system of molecules that will change position, but you're always keeping track of the same amount of substance. It's the same concept here. So what this says, written in continuum notation, is the integral over this volume, and this volume is a function of time, so it's evolving in some time, of the density dV. So that's describing this blob. So this is the mass of this blob, if you like. So let's say mass of this system is equal to the integral rho dV, and that will basically, as a function of time, be equal to 0. So again, it's the same argument. We're following the same selection of molecules. So because we're following always the same selection of molecules, trivially, mass is conserved. There's a subtlety here just to note that this density integrated over volume is the mass, in the same way this is just trivially the mass. When we talk about the continuum, we're always talking in terms of densities. Densities at each unit point. So does that make sense? As a concept, you can see they're similar. At least this is just a kind of statement of the conservation of mass. So for a molecular system, it's entirely possible to follow an arbitrary collection of molecules, and you could track them, and you could look at them, and you could analyze certain properties. And certainly for things like if you covered autocorrelation functions of velocities or the Einstein relation for position, you'll get diffusion, for example, from something like that. By following each of the molecules, you can see how far they diffuse. So this type of Lagrangian reference frame in a molecular system is often useful. In a continuum, this is pretty much untenable. So it works for solid mechanics, because with a solid, you imagine you've got a test piece, it will only deform slightly. So following this kind of deforming object is easy enough to do mathematically and conceptually. With a fluid, very, very quickly, this would become so fragmented and complex that you would actually not be able to follow it. So a Lagrangian reference frame in fluid dynamics is pretty much not possible to use. So what we do instead is we actually re-express this system instead as basically a fixed volume in space where we watch what goes through. So this is this idea of going from this Lagrangian reference frame to an Eulerian reference frame. So mathematically what we're going to do is we're basically going to expand out this expression. So if you acknowledge the fact that the integral itself is a function of time, you can think of this being like chain rule. So if we do d by dt of two functions, function f of t and h of t, you've seen before that this then you can expand out as f of t dh by dt plus h df by dt. So we can effectively treat this in that way, just using this kind of chain rule property. So we're going to do the same thing. We're actually going to expand this out. So what we get from doing that is we're going to treat, first of all, the time derivative of density, d by dt, dv, plus, so what we're doing here is we're actually taking, if you like, dv by dt of rho. So I'll leave that for the moment. So we're effectively using this kind of concept of chain rule, where one of the things we're actually analysing is the way the volume itself is changing, if you like. So there's a far more rigorous way you can show this, but I mean, this is a kind of just physical argument. Hopefully you can just appreciate this. Okay, so this volume here, we're looking at the change in volume as a function of time. So if you think of volume as a function of time, in order to like analyze the volume, let's say the volume was a sphere, for example, the derivative of a sphere with respect to, say, position would give you the surface area. So we actually need to kind of re-express dv by dt using, so let me just write this out. So the other mathematical property is if you're doing, say, d by dt of some function of time, you would then write that as dh by dt df by dh. So it's kind of implicit differentiation. Does that make sense? You've all seen this before as well. So these are the kind of two mathematical tricks for just dealing with derivatives. So we're going to use the same idea here, where we're going to write, the time evolution of the volume as being the position, if you like, so vectorial position of the volume by dt times dv by dr, if you like. So we're basically just writing an expression for how the volume is going to evolve in time. And then this dv by dr is effectively going to be a kind of surface. So you think about the derivative of a volume, it will give you the surface area, if you like. So this is an expression for the surface. And again, these are kind of slightly hand-wavy arguments, but what you end up with then here is we're going to call this ds. So this is an integral then. This becomes an integral over the surface. This expression here becomes u, and this expression here we're going to call ds. So we end up with u, which is a vector, dotted with ds. So sorry, this is a dot product here because we're actually treating the vector directly. So I appreciate this step's a little bit of a leap of faith, but just conceptually you can at least see what's happening here is that we're actually considering both the evolution of density inside the volume due to a change, and then also this term that describes the evolution of the volume, and that we're actually re-expressing as a velocity dotted with the change in the surface, if you like. So then if we re-express our terms like this, we end up with this equation. So this is basically a form of what's called mass continuity. So it's just a statement of conservation of mass. So it's saying that the change in mass inside a volume is equal to the flow over the surface. Now hopefully you can appreciate this. So let's say we look at a molecular system and we were to draw, say, an arbitrary volume like this. The change in the particles inside the system will actually be equal to what flows over the surface. So if one particle flows in and one flows out, so we're counting what flows over the surface, the net contribution inside will still be equal to 2. So you can see it's basically just keeping track of particle counting, but in a kind of continuum sense. We also have to use another mathematical trick here, so we're going to use what's called Divergence Theorem. That this allows us to rewrite A dot ds. Let's stick with the same notation. So let's h. We need a vector today. Okay, some vector A dot ds we can actually write as the volume integral of divergence of A. Like that. I'm hoping have you seen this before as well, right? Divergence theorem, or okay. So for now, these what's here is basically just kind of well-established mathematical tricks. So just accept them, look them up afterwards if you're not entirely convinced by them, but they're kind of established. Okay, so then this allows us to re-express. Can you guys see? Yeah, it's fine. So now we can express the volume d rho by dt plus divergence dot rho u dv. So now we have here an expression using this trick where we've rewritten the surface flux as the divergence inside the volume for some arbitrary volume. Okay, so the final step in this process is then actually to take the limiting case. So what we're going to do is we're going to take the limit that the volume tends to 0. So what we're going to do is we're going to basically keep shrinking that volume, because it's arbitrary anyway, until it's a single point in space. So bear in mind, this is where the continuum assumption actually becomes important. What we're saying here is that actually, this conservation law of mass for some arbitrary volume is actually valid when we zoom in to any individual point. And this is where, by assuming a continuum, we can play tricks like this, which means that this limiting case, so that's not strictly equal to that anymore. So let me just rewrite this. So let's keep that as it is. And then this is a new statement. So we're saying the limit as v tends to 0 of this integral expression d rho dt plus divergence of rho u dv will give you effectively a differential equation, d rho by dt plus del dot rho u. And this is mass continuity equation. And if you like, you could have rewritten this in vector notation. So this would be dx I rho u I. So you can see it's actually a sum over all 3 terms, d rho dt. Does that make sense? Any questions about that? Or? Okay, great. Here you mean? This. Oh. So this is, sorry, this like that. That's just a divergence. Yeah, sorry, bad penmanship. Yeah, so sorry, this is just the divergence operator. So, I mean, again, this is something you can show mathematically, but the way to think of this is that, and actually, what people often do is they actually define divergence of A to actually be the limiting case of V tends to 0 of the surface A dot ds. So this idea that if you've got some volume where you've got flow over a surface and you shrink it down to a point, that's actually the definition. So this is a definition of the divergence. So the divergence itself is actually kind of defined in this way. So this relationship between the two, they're kind of saying the same thing. One is kind of a point-wise description of this. Sorry, this is missing a dv here. So the idea is this is inside a volume. Okay, so what we're going to do is we're going to repeat the same process now for the mass. So it's for Newton's law, effectively. So, okay, to rub this out? Yeah. Cool. Okay. So, the argument goes almost exactly the same. Instead, now we're talking about the momentum, rho u dv, inside this volume as a function of time. And for our molecules, each of the molecules are actually interested in the sum from I equals 1 to n for the system of mass times velocity, if you like. Now, because with Newton's law, it actually says that the acceleration or momentum change of a particle is due to forces acting from outside. So it's a statement effectively of they use impressed force in original Newtonian mechanics. So it's this idea of particles with forces acting from external sources. So that says the momentum change would be equal to 0 in the absence of forces, whereas for Newton's second law, you effectively have a momentum change that's due to the force acting on those particles. Now in this particular case, because it's a sum of particles, we also have to add up the sum of all forces acting on each of those particles. So conceptually what you can see here is, for this collection of particles we have forces acting over the surface. So it's all of the forces acting over the surface. All of the forces internally will actually be equal and opposite and cancel out. So we can actually express this as sum I equals 1 to ns, sum j not equal to I of n fij. So this is basically a statement that the momentum change will be equal to all of the forces acting over the surface. So the continuum equivalent of this is we're saying that the time evolution, rho as a function of time, rho u, dv is equal to the forces acting over the surface of that volume. So again, by the same argument, it's all of the kind of forces of interaction with the surrounding fluid, if you like. So how all of these interactions. And we know from the molecular dynamics those forces of interactions are effectively the kind of intermolecular forces. In a continuum, that's where the constitutive laws come in, and we'll talk about that in a sec. Okay, so again, this is a Lagrangian reference frame. This is saying that the volume as it deforms in space is going to be shaped by these kind of forces acting from outside. And again, this is unusable in a kind of continuum in a continuum because you can't actually follow this volume as it evolves. So what you do is exactly the same trick again, where we actually expand this out using chain rule. So we're going to rewrite this left-hand side as the integral over volume of d by dt of rho u dv plus, if you remember the same argument again, we have the second term, which is actually the derivative of the volume, where we're again using this idea that we're going to rewrite it as u dot ds. We end up with an expression at surface rho u, and then we get a u dot ds term again. So again, physically, conceptually, it's doing exactly the same thing. It's counting the momentum carried by any exchange of fluid crossing the surface. So at a molecular point of view, you could think if a particle for a fixed reference frame is able to leave, then it will carry some momentum out of that control volume, if you like. So. Okay, does that seem reasonable? So this is what's called Reynolds transport theorem. So it's effectively a statement that goes from following a collection of fluid to expressing that in a reference frame that's fixed in space and looking at what the change inside plus what flows over the surface, which is a far, far more convenient way to work in fluid dynamics. And you've already seen this. When you're doing a numerical simulation, you're actually using an individual series of fixed points, and you're actually modelling kind of diffusion over them, for example. So those pictures you're getting where you see spreading, it's because each of the points is effectively seeing what spreads over that surface. Use the same trick again, this divergence theorem, to re-express everything as an integral under a volume. Plus divergence of rho u u, all inside dv. And again, we're going to take the limiting case. So in a limit that v tends to 0 of this volume, I'll write it in index notation just to show you the other possibilities. D by dxj rho u I u j dv. So it's exactly the same expression, just written in index notation. And you can see this kind of repeated index implies multiplication, but you still have this free index here because it's a vector equation. So it's describing momentum in 3 components, u, v, and w. So then we actually get to an expression that's d rho u by dt plus d by dx j rho ui u j. Yeah, in that limiting case. So that is hopefully you're recognizing at least the left-hand side now of the. So this is the basically what I've just written here, and then you can see hopefully now we've effectively got the left-hand side, and then that limiting case will give you the left-hand side of the Navier-Stokes equation, as we've seen it before.
So, then these two integrals describes like the changing deformation of the whole system plus the changing momentum inside the system.
So sorry, this.
These two integrals that you wrote, like in the second step.
Here you mean, yeah? Yep. Okay,
The
so. Yeah. So let's say this is if you like the Lagrangian, and then this is now written Eulerian. So there's two things here. I mean, mathematically, you're doing just a process that's just a way of re-expressing something. So you could actually just solve this equation. This is a complete equation. To be consistent, I probably should just make it clear that this is actually the left-hand side. So we're actually just but this would also be equal to f of s, if you like, at each point. So if it was possible, we could solve this equation directly. But instead, what we do is this mathematical process that gives us this. So in just a purely mathematical sense, that's just a series of operations. Conceptually, what you're doing is you're actually going from following the entire collection of particles each time step and the way they deform, to actually rewriting it in a separate form that actually makes it easier to treat. So then, written in this form, it means that because you've multiplied out, you actually don't need to follow the change in volume. You can use a fixed volume there. That volume, as a function of time, is no longer important, which means you can actually treat a fixed volume, and it's a far more useful way of doing things. So the reason for doing this is because it's useful. Certainly, if you work with solid mechanics, you'll use actually this form of the equations and actually follow, a very slightly deforming element. In fluid dynamics, it's not possible. So then instead we rewrite it in this form. That is I mean, the way to think of this is actually just, think of a fixed cube. Because we can choose an arbitrary shape, cube's probably the easiest to work with, certainly with the context of solving numerical solutions if we're working with a cube. If you're thinking of a fixed cube in both cases, then we can actually just look at what flows over the surface of that cube. So rho uu, and then we're actually interested in, d rho by dt inside. So we can just take any arbitrary shape now in this particular reference frame, and we can just look at what flows in and out in that form. Does that make sense? Sorry, to answer your question? Maybe not. So sorry, ask me again, was it?
Yeah, it was just like basically what you are describing in its integral. It's like the...
Oh, I see. Okay, so this integral is integral over volume of the change in momentum inside that volume. So that's how momentum changes inside the volume. This term is basically how momentum is carried across the surface of the volume. So maybe it's easy to think of in terms of molecules. If you had a molecule, it has an associated momentum, mi, vi, if you like. If this molecule was to flow into your volume, it would actually bring some momentum into your fixed volume. It would kind of carry it in. So in order to actually keep track of these equations, you would actually have to be taking into account those terms. So if you look at the Irvin and Kirkwood process, it actually gives you a molecular form of this, where it's counting the molecules flowing in. And yeah, so I mean, the statement of Newton's law is you can think of it as being momentum change inside the volume is equal to momentum carried by particles entering and leaving, plus the forces acting from outside. This is exactly the same statement. Momentum change inside the volume is equal to the momentum carried by a flow into and out of the volume, plus the forces acting from outside. So it is just a statement of Newton's law. So provided you accept Newton's law, then this is just a re-expression of that same conservation. In the same way what I showed you before was a statement of conservation of mass, keeping track of numbers of particles. This now is a property of the particles, if you like. They have momentum. So that should be a vector. So should that. So should that. Okay. So that's the left-hand side. You can, do I do that? So you can re-express this in the form we've seen. So if you remember, the actual form we see in the equations of motion is sort of rho du dt plus u dot del u. And then we divide both sides by u. You can actually show this by basically just using chain rule on these various terms and then assuming incompressibility. But I'm going to skip that just because it's purely just mathematics. There's nothing there that's tricky. It's just a case of manipulating the form that we use. And like I say, you'll see it written in all sorts of forms. So in some textbooks, you might see it written in this form. In some textbooks, this form, and so on. So I personally, ambivalent as to the form. Okay. So then I mentioned last week that you can actually do the same thing for molecular dynamics. So if you apply the same trick in molecular dynamics, it's the same as multiplying this equation here by like a Dirac delta function. So if we stick a Dirac delta function on both sides of this equation, it has the same action as basically taking an arbitrary collection of particles and saying, actually, we're only interested in the particles, at some arbitrary point r. So we can then basically work through exactly the same process as this for a molecular dynamic system, and then you can define things like density, momentum, work through the mathematics, and you can get terms that are, change inside a volume, plus flow over the surface of a volume, plus forces acting from outside of that volume. So the Dirac delta function would be key to kind of getting that same process working for a molecular system. I'm not going to go through that because this is the continuum part of this course, but just to understand that these assumptions that we've made, that you can define a field at any point in space, end up creating a Dirac delta function in a discrete system, which, like I said, a paper by Irvin and Kirkwood is very nice if you're working in this area or plan to. Okay, so the next step is to deal with the right-hand side of this. So let's move on to that.
Hi.
Yeah, sure.
Try to
Yes, yes.
I guess we should add d over dt be constant.
You're absolutely right. Thank you. Yeah. Sorry. Good point. Thank you. Yep. Absolutely right. Yep. Sorry. Yeah. Yeah. So I'm just going to state that for now. If you're interested in just this link, you have to assume divergence of u is equal to 0, and then just basically expand this out using chain rule, and you can show by assuming incompressibility condition that those two are equivalent, if you like. But it's not particularly illuminating; it's just mathematics. Okay, so now we're going to talk about the right-hand side, which I showed you kind of a lot of the steps. So I've uploaded a couple of things online. There's this sort of photographs of the set of notes I had before that give quite a nice description of the various assumptions. There's also a discussion of Stokes' law. It's probably more in depth than you're ever going to need, but it's quite a nice kind of philosophical discussion, if you like that kind of thing. So if you want to know more about these kind of various steps, then you can look at that. Okay, so let's think about the right-hand side. So these pictures are getting a bit crowded, so let's start again. Okay, so let's now define, because we're happy with our volume being fixed in space, we're going to define them both as cubes. And you can think of, again, a series of particles. Okay, and then we had this term that's basically Fs. So we're interested in basically working out in a continuum what Fs is. For our molecular system, that Fs is simply the forces acting over the surface from all of the external molecules. So in a molecular system, we actually have all of the terms that describe those forces. And we can split this into two terms. So there's the action of particles that effectively move into and then back out. So typically, to go from a molecular system to a continuum, we're taking either an ensemble average or an average in time. Now, over time, what you'll see is that this kind of Boltzmann's idea of particles bouncing off the surface of a volume give you a form of pressure. So what you can imagine that's doing is it's a molecule entering a volume, imparting some momentum inside and leaving again. So that gives you the kinetic part of your pressure, if you like. You then have these kind of contributions to what's called the configurational pressure from a molecular system. And these are effectively like the spring mass system. So it's like if you imagine a spring between two molecules or the potential like that, you can imagine that there is effectively a contribution to pressure due to those kind of intermolecular forces acting from outside. So that is the Fs, the sum, is equal to the sum I equals 1 to n, j not equal to I to n, of Fij acting over those surfaces. So in a molecular system, we know all of that, and we can split into various parts. In the continuum, we have absolutely no idea as to what those terms are, and we have to approximate them in some way. So typically what we do first of all is we actually rewrite this in terms of a stress tensor. So we actually split it into the contributions over the various surfaces. So we can express this as, if you like, a stress tensor dot ds. So that's the stress acting over each of the individual surfaces. And we'd have a stress contribution on each, maybe a traction. So you can think of this kind of total force as being split into the force acting over each of the individual surfaces. And then we'd rewrite that using this divergence theorem as a divergence of some stress tensor. So that was the form we saw at the end here. So it's the divergence of some stress tensor in both systems. So it's not clear from looking at this why you'd want to do that, but it's really to kind of start to break this complicated force, that's all of the interactions from outside, into kind of manageable contributions. So then you can split it into direct contributions and shear contributions, and then start to approximate those effectively. Okay. So if you remember, I'm saying that the molecular stress, so if they say it's a molecular, it actually contributes to a kinetic part plus a configurational part. So you've got the two contributions. What we're going to do is we're actually going to approximate our stress in our continuum system. We have to think of some way to actually get this value. So we're going to actually approximate this in the same way. We're going to say it's going to be made up of a kinetic part, if you like, dp. Actually, I'm going to use index notation. So it's ij, and then we have basically this identity. Have you've seen this before, the identity matrix? Okay, so this is okay. I'll just complete this. So this is basically the equivalent of 1 in tensor notation. So it's a vector that's 0 and off the indexes and 1 there. So this is a statement that the pressure is only acting in a direct sense as part of your tensor. Again, don't worry too much about the details of this. And then we've got our shear stress component. So in the same way that we know that there are two contributions at the molecular scale, we're saying there's a kinetic part, which is just a kind of scalar pressure, and then some expression here for shear stress that's due to all of the molecular interactions. Now, because we're not doing a full molecular simulation, we have absolutely no idea what they're going to be. So we have to basically make an approximation for this term in some way. Now, if you think about what we actually know in our equation is in terms of velocities. So ideally, we'd want to be able to express this term in terms of the velocities, which means we can then use the previous time steps velocities to approximate that. So, the question really is, how do we write this as some function of velocity and maybe pressure? Because we've already split the pressure out, this is just going to be a function of velocity. So this really is the kind of, the starting point, I guess, for people trying to derive an equation that's useful, because we don't actually know this expression. Okay. So the first step in this, and this is all just a series of assumptions, but we actually approximate this as the first term in a kind of expansion. If you like, you could actually take higher order terms, which would be in powers of basically even higher dimensionality. In some of the work I've actually done, we've actually had to include higher order terms. So when you start to look at extreme conditions, actually this assumption starts to break down when you have very high shear rates, for example. But certainly in most cases of interest, this is a reasonable assumption. So this is assuming, if you like, a linear relationship between stress and strain. So this is kind of the same assumption in some ways as Hooke's law. If the force is equal to like a spring constant times the extension. This is saying the same thing. We're actually saying that the stress tensor is equal to some horrible 81 component coefficient that's essentially constant, and then the strain rate. And that strain rate here is basically just the divergence of velocity with respect to x. So you've used Hooke's law, right? Years ago, I guess. So you've got like this idea that the force acting on a spring is equal to some constant times x. So, and this idea that it's kind of linearly proportional. If you like, this is kind of a much more complicated statement of the same thing. What we're saying is that epsilon is kind of like x in this case. So you can hopefully appreciate that this is like the strain. So it's the difference in the change in velocity, if you like. So the way velocity is being strained in the fluid. This constant is this, which although is 81 components, is just a constant in the same way. And that, in principle, gives you some closure that will tell you what your force is, which then, in turn, will allow us to actually approximate the right-hand side of the Navier-Stokes equation. Okay. So the next step is to try to get this 81 component tensor down to something that's more manageable. And certainly there are uses where people will treat a kind of larger set of these, but for our purposes here, we're making assumptions of an isotropic fluid, symmetric stress and strain tensors, and this allows us to actually express this component as lambda kk ij plus 2 mu. So although this still looks complicated, this is now only two coefficients, so these are constants. This here is the trace of the tensor, if you like. So we've seen that before, that's the sum over the components in the tensor, and then this mu term here. So the next assumption that's made is what's called Stokes' hypothesis, and this allows us to reduce these two coefficients to 1. So it's a statement that if 3 lambda plus 2 mu is equal to 0, then we can actually rearrange and we can get an expression for lambda in terms of mu. So we can say lambda is then equal to, is that right? Something feels wrong about this. Anyway. So lambda is equal to minus 2 mu over 3, for example. So we make this assumption effectively, and this is Stokes' hypothesis, which means it's not proven. Again, it's another assumption in this kind of chain of assumptions. And the reason it's valid is because it works in some extent for many cases. And then also implicitly we're assuming these kind of viscosity coefficients are the same for all points in the fluid and all fluids. Okay. So then this actually allows us to rewrite this as minus 2 thirds mu k ij plus 2 mu epsilon ij. So now we've only got a single coefficient. The final assumption we make is incompressibility, and this is kind of optional. It works very well for most dense fluids, certainly for water, at anything less than about Mach 0.3. This is a reasonable approximation. And this incompressibility effectively says that d dot u is equal to 0, which in vector notation is du di. And again, it's just mathematics to actually work through. But you can show that if you do d by d xj, and you take each of these individual terms, yeah, it's not worth me going through. Yeah, so I won't. I'll just state that because it's going to end up being far too involved for this part of the board. So if you want, you can work through that to actually check that that's true, and you end up with just a single coefficient. Okay, so what that means is we can then re-express the original form that we wrote, that was, if you remember, pi ij, which is equal to minus p times this identity matrix. It just says it's just the diagonals of the tensor, plus mu d2 ui by dxj dxj. Sorry. So that's like that, and then what we're doing is we're taking a derivative of both sides. So that's dxj, sorry, and then this ends up basically being dp dxi, and this is dxj, second derivative. Okay, so this entire process is going from the forces that we don't know to a closure relationship that allows us to relate those unknown forces to some expression in terms of velocities. And we start off with a kind of this 81 component tensor that relates the velocities to the stresses, and then we work through this process making a series of assumptions that eventually gets us down to one scalar pressure and then a single viscosity coefficient for a fluid. And this viscosity coefficient is what you obtain from doing the kind of green kubo and manipulation in molecular dynamics. And like I say, at any point in this process, you could have stopped and you could see the validity of your assumptions by comparing to molecular dynamics. Okay, I mean, is that clearer or worse? More unclear? I mean, this is, again, like I say, it's a lot to cover, but hopefully if you're planning to work in fluid dynamics, it's at least a good introduction to that. Without knowing the kind of, having done all these kind of vector manipulations, it's not going to be clear. My suggestion would be, if you're interested, to work through this yourself. So find a textbook and actually work through each step yourself, go through. It relies on you having, you know, reasonable ability to manipulate these vectors, but for me, the key point is the assumptions, because everything else is just mathematics. So, you know, this idea that there are, on the left-hand side at least, it's purely just manipulation of reference frame. On the right-hand side, that's where you're making these assumptions, and that's where it's interesting when you start comparing to molecular dynamics, because then you've got the differences and, you know, this kind of idea of stress being linear function of strain rate and isotropy of fluids and Stokes hypothesis. Yeah. Any questions? Or? Yeah, sure.
This is like a curiosity, but I was like, the other day, we were like, normally you get like properties from molecular dynamics, and then you can use them in fluid dynamics.
Yeah.
Is it possible also the other way around?
So there's a field of kind of research where people do this kind of two-way approach where let's imagine you had a large continuum simulation with very complex molecules that you couldn't predict with this single coefficient, or the coefficient would be varying in space. What you could do is you could have a really complicated flow field where on a large scale this flow is impossible to model with pure molecular dynamics because it's too large, you know, meters or whatever else. And you could actually take a single region in that space. You could run a molecular dynamics simulation with that flow field. So you actually enforce the kind of velocity from the CFD here, velocity from the CFD, and then you actually get the viscosity within that flow field. So the idea is that you're saying the flow field is massive, it's on, you know, billions of molecule scale, but we're actually taking a small subsection. We're looking at that. We're getting the viscosity in this particular condition from the MD, and then we're feeding that back into the continuum as a refinement. So you effectively have this kind of combined iterative process. So there's certainly research that does that. It's not common, and certainly not in anything in industry, because it's very complicated to kind of link those two, and you've effectively got two separate areas of research kind of coming together. But yeah, I mean, there's certainly that type of thing is possible. It's all a question of kind of horses for courses. What's useful in the different, so the relative kind of uses of the two different modelling techniques. So molecular dynamics, like you say, is very good for getting viscosity, is very good for getting kind of equations of state, transport properties, but it's limited to very small system sizes and only works, yeah, it's very difficult. So things like turbulence, for example, you couldn't model easily with molecular dynamics. You know, I ran a turbulence simulation, it took about a year on a supercomputer. Oh yeah, well over that, like running and checking results and stuff. To take a molecular system in C turbulence. So this idea of complex, you know, chaotic motions, because it's too small. You know, you have to do like 300 million molecules. You have to run it for a very, very long time. You could do it on a desktop computer in like a couple of hours. So, you know, in many ways, Continuum it actually works really well. One thing I was going to show you actually is something from my. So I'll show you some results from a molecular dynamics code. So when we talked yesterday, we looked at Poisson flow. So that was basically flow in a channel where you have a pressure gradient and you see a parabolic velocity profile. What I was going to show you is actually a molecular dynamics simulation and a comparison of the same case. So we have a molecular dynamics channel, we have a pressure gradient, and we look at what happens in that same case. So let me. What's where the remote is? Oh, here we go. Okay. Okay, fantastic. So, if you remember yesterday, we looked at this particular case of unsteady diffusion with forcing at the end of yesterday's lecture. And the idea is that you get this velocity profile that's kind of parabolic. So this is the top and bottom of the channel. And you see, because of this this pressure gradient, what you see is the fluid evolves and eventually reaches this kind of steady state parabolic profile in that way. So what you can see is if you do the same setup in a molecular dynamics simulation, okay, so this is the same. I don't know if you saw anything like this, but this is kind of a channel in a molecular dynamics system. So you've got fixed molecules on the top and bottom. So you kind of set them to a lattice, effectively, of molecules. And then you've got just a fluid of molecules in between, and you apply a pressure gradient. You have periodic boundaries. Did you do any cases like this with channels in? Okay, so this is kind of an example of molecular fluid dynamics, if you like. So you're modelling the same setup, this idea of fixed walls, where the velocity is 0 at the walls. You apply some pressure gradient that's actually driving the flow kind of in this direction. And then what you're seeing is the overall bulk motion of the molecules is kind of driven by that pressure gradient. So let me show you then the average. So then what we can do is we can take that field and we can average it locally in space to look at, say, velocity and density in that field. So I've just done that. Okay, so here are now the results. So if we look at a contour plot, this is a contour plot of, say, velocity in the channel. So you can see the velocity is kind of 0 at the top and larger in the middle. Bear in mind there's a lot of noise now. Because this is a molecular simulation, instantaneously you've kind of got fluctuations which are kind of due to temperature and random motions. But if we look at the profile that you get in the y direction, so this is between the walls, you can see we actually have the same parabolic profile. And this is probably about 5 nanometers. So this is a kind of really tiny channel where we're applying, Newton's law, solving that with fixed walls, and we're seeing exactly the same behavior you'd see in a continuum. So, this obviously took far, far longer than it would take to do a continuum solution, but it's giving the same behavior. And what you'll see is, depending on the fluid you choose, you actually have the same viscosity and the same overall kind of fluid dynamics behavior. So the argument goes that there's no reason to simulate it at the molecular scale if you can get the same behavior in a continuum. If you look at the molecular dynamics, you can also look at things like, for example, density. So you can see, we talked about incompressibility, which is kind of like assuming constant density. You can see typically in the middle of the channel, that's fairly reasonable. Near the walls, you start to see kind of stacking effects, and this is kind of the lattice of the walls. And what you see is actually, it doesn't go straight to being a fluid. There's kind of a transition region where it sticks, slips, and you get this kind of complicated behavior. But on the whole, at least when the channel's big enough, this isn't a problem. And then you can look at other things, for example, temperature, which again I mentioned that fluid dynamics is typically isothermal, so the temperature is unimportant. And this is kind of again backed up by the molecular dynamics in that you have a kind of pretty much constant temperature across your channel. So in other words, you can do a molecular simulation of, say, the same fluid dynamics cases of interest, these kind of channels, whatever else. But typically the assumptions you're making, for example, temperature is constant or isothermal, density is fairly constant, your viscosity is a single coefficient, are all fairly reasonable, even down to kind of 5 nanometers. So in other words, why bother simulating more than you need to? If you can get the same behavior that you're interested in from fluid dynamics, then why go through the full molecular simulation, which is far more expensive? And don't get me wrong, there are certain cases where that's useful. So if you remember the video I showed you on the first day, that was kind of, I mean, that in some ways is a summary of the cases I work on that where molecular dynamics kind of broke down. Continuum mechanics breaks down. So if you remember, there was the example of, so this is kind of a channel. You know, you've got the molecular detail and you've got kind of sliding walls. And as I mentioned, you've kind of got this density stacking or stick slip, and then it's the structure that's actually causing the viscosity. Notice, by the way, how little individual molecules move. It's like a really large amount of structure. So this was kind of the large simulation. So if you push it far enough, you start to see turbulence. But like I say, this took a year to run on a supercomputer, whereas you can do it on a desktop in the Continuum. And largely speaking, the two results are identical. You can see the kind of streaks and the evolution of these complicated structures are actually fairly similar between the two methods. So again, CFD is extremely useful for kind of accelerating this kind of molecular scale detail. The cases where I'd say molecular dynamics starts to become important is things like phase change. So you can model, nucleation of droplets. That's very, very difficult to do with a continuum. Typically, you'd have to then start sticking coefficients in. So again, the rate of phase change in nucleation is given by coefficients that would either come from experiments or from molecular simulation. And you can start to look at complex molecules. So if you have, two-phase flows, complicated molecules, those type of things, the continuum assumption then starts to break down, and it's worth looking at more complicated cases. And then finally, this idea of heating. So when you have nucleation of bubbles, and you can see you get kind of complex behavior like that. But yeah, so it's a case of, choosing the right model for the right situation. I think this course is very much about that. But, certainly if you're interested in turbulence, large-scale fluid behaviors, the continuum is a much more efficient and sensible way to go. If you're interested in equations of state, getting actual coefficients from first principles, molecular dynamics is the way to go. If you're interested in the interaction between molecules, quantum mechanics, I guess, is then probably the level you need to go to, or chemical reactions. But it's all about what you want to look at, effectively. Yeah. So any other questions on that? So I think the rest of the session, the plan is just to work on the assessment, and I'll be around to help out.